nonmetals, right? So that is really the way to recognize an ionic compound. If the first element is a metal, then you know it's ionic. So this is a metal and a nonmetal. And you can identify metals and nonmetals. You'll always have a periodic table. And what do you look at on the periodic table? The little zigzag line. So the zigzag line is what separates metals and nonmetals. Metals are to the left of the zigzag line, nonmetals to the right. So if you see elements on opposite sides, then you know that it's an ionic compound. So when trying to figure out the formula for them, you have to assign the element a charge. What always happens to the metals? Do they gain or lose? What happens to their charge? Things like sodium and potassium, calcium. No? So what happens to their charge? Metals always what? They're always positive because they lose electrons, right? So remember that when you assign the charge, metals are always going to lose electrons because they don't have very many. And you can tell their charge by their group number. The group in front of the capital A at the top of the column, that will tell you the charge. Okay, so when looking at lithium, sodium, potassium, group 1A, +1. When looking at magnesium, beryllium, and calcium, that's group 2A, +2. Okay, so all the way at the very top, whatever that number is in front of the capital A, that tells you the charge on the metal. What do you know about the nonmetals?
They gain electrons.
They're the ones that gain electrons. So, nonmetals, they're going to gain electrons. So you can figure out their charge. They're going to be negatively charged. So the ones over on that far right side above the zigzag line, find the group number. That's all the way at the top. So take the group number -8 will tell you their negative charge. So nonmetals gain electrons. So here, well, I guess they say it should be this way. So the group number, whatever is in front of that capital A, see at the top of the column, their group number -8 will tell you their charge. So chlorine, group 7, 7 minus 8 is a -1. Oxygen, group 6, 6 minus 8 tells you it's a -2. So there's the slide that I pulled up. This is really the one that you can go back to refer to kind of refresh. But you really don't have to memorize what the charge on these ions are. You just have to remember to look at the group number at the top. Everything in that first column +1, it's in group 1A. Everything in the second column is +2, but you see that it's group 2A. So the number in front of that capital A will tell you the charge for the metals. The number on the top in front of the A for the nonmetals, you just have to figure out how many does it gain to make that 8. So take the group number -8 in order to figure out what the negative charge is for nitrogen, phosphorus, oxygen, sulfur, all those nonmetals over on that far right side. Come back. So when you write it, what element you always list first in a name? It's always the metal, right? Metal's always first, then the nonmetal. So just remember sodium chloride. Best example, because it's one that's super familiar. So you always write the metal first, then the nonmetal. That looks like nom. Then the nonmetal. Naming rule, you always use what? The full name of the metal. That's the first word in your ionic compound. And then you're going to add the second word. Yep. First part of the nonmetal plus IDE. So like I said, the one that we talked about last time first, NaCl. Sodium is always listed first, and you would call that sodium chloride. So I noticed that a lot of people like did these ones first. Okay, so like K2S, Li3P, these ones, if you're going to name, just follow that rule. So what would be the name of the first one? K is potassium. You use the first part of sulfur, so it's sulfide. Li3P? BEF2? CA3N2? So you just follow that naming rule. Whole name of the metal, first part of the nonmetal, IDE at the end. If you want to try and figure out the formula from the name, then you have to assign charges to figure out what the ratio is of positive and negative charges. So sodium nitrite, so sodium is Na, nitrite is N, right? So first, go from what the name is to the symbol. And remember that I won't give you any other than the ones that are like 1 through 20, the ones that you had in the list. So you won't expect to see like strange, odd ones. Like I won't give you Ba, even though that's barium, just because I didn't give it to you as one of the ones to learn names and symbols. So you can expect to see the ones that you had in chapter 1, the 30 that you had to name. In this second step, assign the charge. So first write the elements, assign the charge. Sodium would be A plus 1, right? It's in group 1A. Nitrogen would be A minus 3. Then you take the number for each charge and swap them, okay? The charge on the metal tells you the number of nonmetals. The charge on the nonmetal tells you the number of metals. So you just take this, and this would be a 1, and this, in order to figure out the formula. Charge on the nonmetal tells you how many metal atoms in the molecule. The charge on the metal tells you the number of nonmetals. Calcium phosphide. Calcium is Ca. Phosphide would be a P for phosphorus. Assign the charges. Calcium is plus 2. It's in group 2, so it's plus 2. The charge on the phosphorus would be negative 3. See, it's in group 5. 5 minus 8 tells you it's a negative 3. Okay? Then just swap them. So the formula would be P2. Assign the charges and just swap them. If they were like 2 and 2, simplify. Okay? So that would be the last thing that you would double check. These ones just stay as is. They're already in the simplest form. Lithium oxide is Li and O. Find lithium, plus 1. Find oxygen, minus 2. So if you swap the charges, yeah, not terrible. Coming back to you. It's been a long weekend. Magnesium iodide. Magnesium's a plus 2. It's in group 2. Iodine is in group 7, so it's a minus 1. Mgi2. Charge on the metal tells you the number of nonmetals and vice versa. Bring it in. Not horrible. We'll keep doing these ones, but I'll save this, I'll post it as well, so you can go back and look at it as, then flip your page. What? No! Try not to kill too many trees, okay? So, then we did the weird ones, okay? So then I said, okay, well, there's these 2 weird exceptions. 2 exceptions, one, transition metals, the other one's the polyatomics. And that's kind of where we ended up with it. Transition metals, iron, chromium, copper, those are the ones really that you need to make sure that you're familiar with, because those are the ones that I'll use in giving you names or formulas. Transition metals can exist in multiple positive charges. So iron can be a +2 or a +3. Chromium can also be a +2 or a +3. Copper can be a +1 or a +2. So because they're in that group that kind of drops down, that's the transition group, that allows them to lose varying numbers of electrons and create stability. So in this, if you just said copper chloride, you wouldn't know which copper form you're talking about. That's where the Roman numerals come in. So you use a Roman numeral, and that tells you the charge on the metal. So from that, you can then work out what the formula is. So when you look at copper 2 chloride, copper is Cu, chlorine is Cl, and it's copper 2, which tells you the charge on the copper is +2. So that is 1. And remember, this is really the chart that I showed you. So it's these 3 here. There's more of them. See, like gold can do this, lead can do this, tin can do this. But these are really the ones that we'll talk about again. We will talk about iron because of its importance in red blood cells. Okay, we'll talk about chromium, its importance in metabolism. So we'll talk about these ones again. So that's why I bring these 3 up. So those 3, you want to remember that they can have more than one possible charge. So in this, oh, I thought I had it. Go back there. So we know that copper is a +2 because of this Roman numeral 2 tells you the charge. Chlorine is a -1. See in the word copper 2 chloride? So in the name, when you write out the words, the 2, that Roman numeral 2 tells you the charge on the copper. So that then you can work out the formula. So now I know copper is a +2, chlorine's a -1. So to figure out the formula, just swap them. So it ends up being CuCl2. The charge on the metal tells you the number of the nonmetals. The charge on the nonmetal tells you the number of metals. So iron 2 nitride. Iron 2 nitride, iron is Fe, nitrogen is N. And it's iron 2, so you know because it's a Roman numeral 2, that is a charge of +2. Now find the nitrogen. What's its charge? -3. It's in group 5. 5 minus 8 tells you that it would have to gain 3 electrons in order to be stable. So when you swap these, Fe3, N2. Now in this one, you've got the formula, so you really got to work back and figure out what's the charge on the chromium. So if I know the formula, I know what would the name of this be without the Roman numeral. So this is chromium sulfide. But I need to know if it's a +2 or a +3. So in this one, the number of each atom, do like a reverse swap, right? Just like, so we've been doing is taking them and swapping down. So take them and swap them back. So we will say then that that means that our chromium's a +3 and our sulfur's a -2. Does that fit? Is that sulfur's charge? When you look at the periodic table, sulfur's under oxygen, so it's group 6. So that's the correct charge, and that's how you can figure out what the charge on the chromium is. So you would use Roman numeral 3.
Oh, that's right. It's either going to be 3 or 4.
Well, that's 2 or 3. Chromium's a 2 or 3. Okay, so in that one, it's kind of like you're working backwards to figure it out. See if you can figure out the last one. First, just give its name. Then figure out what the charges are so that then you know the Roman numerals. So what would FeF3 be? Just as a name, general name. Iron fluoride. I left a lot of room, but we're going to put in some Roman numerals. It's a +3. Do you see that if I do the reverse swap, the fluorine becomes a -1, the iron becomes a +3, taking them and reversing them? Is that fluorine's charge? When you look at the periodic table, is fluorine a -1? Yeah, so then that's valid. Now, if you did one and you did a reverse swap, and they were like, if they were one where they simplified to figure out the ratio, you may have to change it. So like if I had CuO, okay, so in this one, if I had, so this should be a 3, but in CuO, I would say, okay, well, that's a 1 and 1, so this would be a +1 and a -1. But what do you know about oxygen? What's oxygen's charge? It's a -2. So when you look at that one, that means that we must have simplified the ratio. So I know this has to be a -2. So what would that have to be? A +2. Okay, because the pluses and minuses have to balance each other out. So this has to be a +2. So this would be copper 2 oxide. I'll try and stick with the ones that don't do that, because it just gets a little complicated then. But that's the reason, because remember, you always try to simplify that ratio if possible. Okay, so then the last one that everybody was like scratching their heads and like staggering out of here last time was the polyatomic. So that's when you have groups of nonmetal atoms that collectively have a charge. So in this first word, second word, okay, so there's still, it's like a metal and a nonmetal. But if you have a polyatomic, then you don't name it according to individual elements, you name it as a group. So in this one, well, again, let's just start with the ones down at the bottom, because those seem to be the ones that people can look at and tell me what the name is. K2SO4. Right. Potassium sulfate. The sulfate ion is SO4 and has a -2 charge. So if you see it, it's just the sulfate ion. This one, the next one, is the only example of a positive polyatomic. Most of the polyatomics come at the end, and they're a group with a bunch of oxygens. But this one is this NH4. The NH4 plus. Notice that it's out front because it is positively charged, like what you would expect a metal to be. NH4 plus is the ammonium ion. So this is NH4 plus or NH4Br, so it would be ammonium bromide. So the non-metal in this one is just Br, so it would again just be a bromide, just like any of the regular ones. But you use ammonium, NH4, together, it's called the ammonium ion. So BeOH parentheses 2. Beryllium is Be, and then OH, hydroxide. So the OH ion is the hydroxide ion. It's got a negative charge. Al2CO33. Aluminum. And the CO33, it's got a -2 charge. It's the carbonate. So you see, like, the carbonate has the carbon with a bunch of oxygens. The sulfate is a sulfur with a bunch of oxygens. The ClO4, that is the chlorate. It's a chlorine with a bunch of oxygens on it. So most of those negative polyatomics, it's a nonmetal with excess numbers of oxygens on them. Okay, so let's do these last 4. So the last ones, these, you've got to write the formula for each, assign them a charge, and then just swap to figure out the ratio. So sodium is Na. The nitrate is NO3, and it has a negative charge. So the nitrate's a -1, and the sodium is +1. So that's it, right? +1 and -1, you swap them, they're still ones, nothing changes. So it would just be NaNO3. Calcium phosphate. Calcium is Ca. Phosphate. It's a 3- or a -3. Don't care which way you write it. I flip back and forth myself. Just 3 negatives somewhere. After that PO4, that's the phosphate. So what's the charge on calcium? +2, right? It's in group 2A. So in this, you take the charges and you swap them to figure out Ca, PO4. This is a 3 and this is a 2. You do have to use those parentheses. So if you have more than one polyatomic, put a parentheses and write the number with the charge on the metal goes outside of the parentheses for that polyatomic. Lithium sulfate. Lithium is Li. Sulfate is the SO4, -2, 2-, whatever. What's the charge on a lithium? +1. So when I swap, what will my formula be? And you don't need any parentheses because the SO4 is just a 1. Okay, so that should look like a 4. Kind of. Sorry. Harassing me. 4. Last one, magnesium chloride. Magnesium is Mg +2, and the chloride is ClO3, and it's a negative charge. I'll go over here. Keep shrinking down. Mg parentheses ClO3 parentheses 2. Okay, so the number, the charge, just swap them, tells you what the number is. And if they were 2 and 2, simplify. Okay, so if you can, if you end up with even numbers with both of them, simplify those. Terrible, not terrible. Can't believe I actually did this. All right. So this is a really good chart. So remember that you do get your little note card. So like with these ones, if remembering which one has what charge, that type of thing, then using this in your listing, or just even adding more examples, that type of thing can help. I don't know if you did any of the dynamic study module, but you should have seen that kind of like had you guessing what charges were based on and ratios and things to try and get you to use this chart really. All right, so we got those, we got the naming, and we got the chlorates, and we'll come back to these. So a bit about these ions. So when you ingest sodium chloride, sodium and chlorine don't stay together. They actually separate into sodium ions and chloride ions, and they float in fluids because they're soluble in water. But they have really important functional jobs. We're going to start talking about covalent bonds, and then we're going to talk about organic molecules, and you'll start to see how important their structural integrity, what their structural importance is. But with ions, it's really their function that they help the body to do specific things. So just some of the big ones. Sodium, okay? Sodium is a huge fluid balancer. If you had chicken wings and fries, some mozzarella last night, okay? So maybe you had some salt with a side of salt for dinner while you're watching the Super Bowl, okay? So when your sodium levels go up because of excessive salt ingestion, what do you notice about your rings or your shoes? Yeah, you feel even like somebody that's not overweight, you end up having like your rings will feel tight, or when you take your socks off, you know how your legs are a little more swollen, your ankles look all skinny. You're like, geez. Okay, that is all because of sodium. So wherever sodium is, water hangs out too. And so if you ingest a lot of sodium, it's going to cause you to retain a lot of fluid. So this is a really big fluid balancer. But your blood vessels are only a certain size. So instead of causing blood pressure to go up, this fluid gets shifted into spaces underneath the skin. And that's why you start to notice like you're kind of puffy. You have some mild edema that occurs. Does it occur forever? No.
Circulate it out.
Yeah. Over time, how do you get rid of it? Pee. Yeah, your kidneys. Okay? And so when you eat things that have a lot of salt, you may notice that you're thirstier. And that's because wherever salt is, it's going to pull water to it. And so then you may drink more fluids, but that increases your blood volume. And so that fluid gets shifted into tissue spaces, like spaces up underneath the skin. And it causes the skin to then swell. For people that have hypertension, this is an issue because that period of time where that blood volume is increasing can affect blood pressure. And so that's why if you have hypertension, doctors' orders are commonly to try and avoid salt. Limit your salt because you're trying to limit that blood volume because increasing blood volume can increase blood pressure. So that's constant in this balancing. As long as your kidneys are functioning and your vessels aren't too reactive, then you can manage and handle it. So you should be like diuresing, getting rid of that salt all during the day. Sodium and potassium together are really important for nerve function, okay? And helping nerve impulses to be sent. Imbalances in sodium or potassium levels are usually felt when you have higher or lower than normal potassium levels because potassium is actually found in very low concentration in the blood. It's found in higher concentration inside of cells. So if your potassium levels go up or your potassium levels go down, you see big changes in nerve function. So low potassium oftentimes can affect muscles. It can cause them to be spastically stimulated and cause you to wake up in the middle of the night with a leg cramp, okay? So if you end up having leg cramps, a common remedy, your mother told you to do what? Eat a banana, okay? Because look at where a source of potassium is bananas. So muscle cramps, if potassium's too low, edema, if salt levels are too high, just examples of how you end up with these changes. Potassium really needs to be strictly regulated. Not only can it affect skeletal muscle function, but it can affect heart function too. So excessive amounts of potassium can cause your heart to just stop. That is actually what they use in a lethal injection. Is they give you a high dose of potassium chloride and it causes the heart to totally stop beating. So excessive potassium inhibits muscle contraction. Low potassium will cause the heart to beat real irregular. So it doesn't beat in a nice steady fashion. It doesn't have that nice strong unison type of beat. It can go, you can start to develop arrhythmias if potassium levels are low. So muscle cramps, heart function, really important. The third one everybody really knows about, calcium. Importance of calcium. Bones, right? Okay, and that's where all your calcium ends up being stored. People that have lower than normal calcium intake end up developing osteoporosis. Okay, they get porous, weak, brittle bones as they get older. They can get spontaneous fractures. But also notice calcium ingestion, especially during childhood, important for development of the enamel of the teeth. This other one that I circled is iron, Fe+2, okay? Not +3, existing in its +2 form. Iron is one of those that's really specific, and it really only goes to one of two types of proteins. Most of them are found where? Where does iron end up? What cell? Your red blood cells. And if you don't get enough iron in your diet, you can end up with anemia. And it's an iron deficient anemia. You're just not ingesting enough. You can't put enough iron in those red blood cells to carry oxygen. So real specific jobs that these ions have, shifts or changes in these ions can end up having physiological changes. We'll talk more about ones like the carbonate, the bicarbonate. We'll talk about the phosphate. So we'll come back to those, but those were just a couple of the ones that I wanted to point out. So these are all ionic. But what happens when you have two elements that have almost identical numbers of valence electrons? So remember, the valence electrons are the electrons in the outer shell. So what if you have a hydrogen all by itself? Remember, hydrogen's in group 1, and it only has one valence electron, like period. It only has one electron. And to be stable, it needs 2. No. Remember, this is the oddball. First energy level only holds 2 electrons. So hydrogen has 1 electron, and to be stable like helium, it needs 1 more. So by this, just a single hydrogen atom, extremely reactive because it needs that 1 more. So if another hydrogen is present, let me move them apart. If there's another hydrogen over here, it has the same attraction for its electron and the same attraction for the other hydrogen's electron. So one can't pull electrons away from the other like we've been talking with ionic, because they have almost the same number of electrons. So the only way that they can create stability is that instead of transferring and forming ions like our ionic bonding, these ones are going to share. So that means that the 2 atoms get close enough together that those electrons spend time with each hydrogen. So the 2 electrons, they're going back and forth. They spend part of the time around one hydrogen, part of the time around the other hydrogen. So you end up with this. They're evenly spanned between, and you could think this hydrogen now it can act like helium. Now it can have 2 electrons in its outer shell, and for hydrogen, that's stability. Same thing with the opposite one. So this hydrogen can behave as if it has 2 electrons and has an electron arrangement like helium. They call that a covalent bond. So very different than ionic. Ionic metals lose their electrons to nonmetals. Here we have hydrogen, 2 hydrogens, and they'll share those electrons to create stability. They call this a single covalent bond because it's 1 pair. One pair of electrons. You may also see it drawn like this with a dash. So the dash represents 2 electrons. So it represents a pair that is shared. So you see covalent bonding when you're talking about atoms that have similar numbers of valence electrons. Okay? Similar numbers of outer electrons, so they can't pull one from the other. Instead, they're going to have to share. And in general, you could say you will see covalent bonding between nonmetals, and also include hydrogen in your list, because hydrogen's sort of the oddball. It's so small.
So it's considered, normally it's considered a metal, but in this situation it's considered a non-metal?
Yeah. Well, and it's because it fits in group 1A because it has 1 valence electron, which is the reason why most periodic tables put it over there. But in reality, it behaves like a nonmetal. Okay?
All right.
So, and it has 1 and only needs 1. So it has almost all the electrons it needs. So it's really more like a halogen in that respect. It only needs 1 electron. So it's really not like sodium. Sodium would need 7 more electrons. Sodium's only got 1 valence electron. And so it'd rather just give it up. But with hydrogen only needs 1 more, so it's not as inclined to give it up because it's so close to being like helium. Okay? So, key thing to remember is now we're talking about these. And this really cuts down, you can ignore all the metals. You're not going to see metals in covalent bonds. All you've got to remember are these ones, okay? And really, it's just group 4, 5, 6, and 7. Those are really the ones that form covalent bonds. Chlorine in group 7. So one chlorine atom, remember that it has 7 electrons, needs 8 to be stable. Because if it can have one more electron, it's going to be just like argon. It's going to be like a noble gas. But the chlorine next to it needs the exact same thing. So you can't pull electrons away. They've got to share. Chlorine in the non-metal category. And so notice that it kind of looks almost like those atoms overlap a little bit. These red electrons, the colored ones that they show, these are the ones that are shared. And you would say that this chlorine now can behave as if it has 8. And this chlorine can behave as if it has 8. A single covalent bond. Now these electrons out here, they call them lone electrons. Those lone pairs. They don't hang out with anybody else. Those electrons belong to that chlorine specifically. Lone electrons do not go back and forth. Lone electrons belong to one atom specifically. So notice the 6 that each chlorine has that are colored in black. So these ones here, those ones belong to that chlorine. The only one that gets shared is the single. And so you always put the shared ones in between, and you would have any non-bonding or lone electron pairs would be included when you draw what's known as a Lewis structure. So this is a Lewis structure where you write each one and the number of electrons around, and you put the shared pairs in the middle. The more we do them, the more we start using dashes because it gets really old doing all the dots. But for the first couple ones, we use the dots just so you can keep track of all of them. Okay? So you always find chlorine has Cl2. So you don't ever see just a single chlorine atom. Chlorine will automatically react with other chlorine atoms to make Cl2. Same thing with hydrogen. Well, we're going there. So looking at the other halogens, bromine, iodine, fluorine, they all are they're called diatomic elements because they always exist in a pair. You're never going to see a single atom of iodine, it's I2. You'll never see a single atom of chlorine, it'll be Cl2, because they can be stable this way. Just exist as a molecule of Cl2, because that way each one can have its 8 electrons.
What was the name of the group again?
Diatomic. So di is 2. There's a couple other ones, but they don't just share one pair. But can you see that the halogens would all share one pair? Fluorine, chlorine, bromine, iodine, because they all have 7 electrons, so they would all share that unpaired electron. Okay, everybody good? Carbon. Carbon is really the biggest covalent bond former. Carbon is the whole reason that you have organic chemistry, because organic chemistry is the study of carbon-containing molecules. Okay, so organic isn't just that they didn't use pesticides and insecticides on your food. Organic originally, carbon was really, like, organic chemistry really refers to molecules that contain carbon. So carbon's in group 4A. So remember I told you with the Lewis dots, spread your dots around. So can you see how carbon can form 4 single bonds? Can you see that it looks like it's got like 1 electron and needs to share? So you could have a shared pair above, below, to the left and the right. But sometimes you need to share more than 1 pair. So you can make a double bond. So a double bond is when you have two electrons from two elements that end up sharing a total of 4. So 2 from this one and 2 from that one, creating 4, which would then add to the other electrons to make that 8. So you can do any kind of variation with carbon, 4 single bonds, 2 single bonds and a double bond, 2 double bonds. You could do a triple bond in a single bond. So carbon can make lots of different types of shapes because of the fact that it always forms 4 bonds. Always. Well, for us, always forms 4 bonds. There's examples where it doesn't, but for us, we're always sticking with the 4 bonds. So let's practice a couple of other ones. So in this, if we had CH4, so if you're given an organic, a covalent molecule, one, you'll always notice that it doesn't have a metal. Okay, so there's no metal, just carbon and hydrogen, non-metals and hydrogen. That tells you it's a covalent molecule. So the steps with this. One, I always list the atoms. And the number of valence electrons. I hate red. A number of bonds needed. So with CH4, I'm like, okay, I got carbon and I got 4 hydrogens. Okay, so I just sort of like break the molecule down into its individual parts. You can figure out the number of valence electrons. Remember, that's the group number. So I know carbon's in group 4A. So that number in front of the capital A at the very top tells you how many. So I know that this has 4 electrons. In order to be a noble gas, like neon, it needs to have how many bonds? 4 more. It has 4 electrons and it needs 4 bonds in order to make 8. And carbon, nitrogen, oxygen, sulfur, fluorine, chlorine, bromine, they're all going to work that way. The only one that doesn't work that way is hydrogen, because hydrogen has how many electrons? Just 1. And how many bonds does it need? Just 1. So I got 4 of them. 1 electron on each. 1 bond needed with each one. So since hydrogen and fluorine, chlorine, and bromine, they only form 1 bond, they'll never be in the middle. They're always kind of like an arm stuck on something else, okay? Because they only ever share 1 pair. So you'll never really see them in the center part. They're always just going to getting attached. So the second thing I always do, I always start with the atom that needs the most bonds. I put that one down first. So when I look at carbon and 4 hydrogens, which needs the most bonds? Carbon. So I'll put carbon down first and I'll put its dots. So there's carbon in the dots. I may have to move my dots around. Sometimes you have to make a double bond or a triple bond, but I always start off and just spread them out. It's nice because I have an eraser. Okay, so you put the atom down needing the most bonds. Then you're going to form a single covalent bond with the remaining atoms to try and achieve the octet. So carbon wants 8, each hydrogen needs 2. So I'll go back and change my color. So I'm going to put a hydrogen here, and I'm going to pair it. Hydrogen here and pair it. Hydrogen here and a hydrogen here. So in each case, I'm making a single covalent bond between carbon and hydrogen. Does this satisfy the hydrogens? Yeah. Each hydrogen now can behave like helium because it can behave like it has 2 electrons. And the carbon in the middle, it has the 8. Okay? So the carbon in the middle behaves as if it has 8 electrons. You could convert those to the dashes. So this chart I have right here really shows your main covalent bonding elements. Carbon, hydrogen, oxygen, and nitrogen. What are those? They're CHON. And what do you know about CHON? Carbon, hydrogen, oxygen, and nitrogen, they make up 96% of the atoms in your body, right? So this is really like the majority of your molecules. They're coming here. Add in the halogens, fluorine, chlorine, bromine, iodine, and then you've also just got sulfur. So those are really the only other ones that you're going to see. But notice across the top, these ones, those are the big covalent bond formers, and they're all in that upper corner. So, H2O, water, hydrogen and oxygen, so you know it's a covalent molecule. No metal in it, it's a covalent molecule, it's just the ones that are over there, plus hydrogen. So in this, we have 2 hydrogens, and 1 oxygen. And you know how I am about oxygen, I like to write oxy, because otherwise it looks like a 0 and that bothers me. Okay, 2 hydrogens and an oxygen, each hydrogen has 1 electron, 1 electron. How many does oxygen have? 6. 6 electrons. Right, so I list my atoms, number of valence electrons. Remember, you can figure that out from the group. Hydrogens, 1 bond. Oxygens needs to make 8. Has to have 2 bonds. It has 6 electrons. It needs 2 bonds to make 8. So that last one, always start with the atom that needs the most number of bonds. So I'll start with oxygen. 1, 2, 3, 4, 5, 6. Just remember in this, you go around, so you'd put singlets, but then you have to start pairing them up if you have more than 4. So you could put your 2 pairs above, below, left, and right. It really doesn't matter. We're going to talk about shapes next time, so that'll help you see why it really doesn't matter where you put them. I just go like 1, 2, 3, 4, and then I start doubling. That's just how I usually do it when I put my dots. But you should pair above, pair below, pair to the left, pair to the right eventually. So now I'm just going to add. So I'm going to add a hydrogen and use one of its electrons. Add a hydrogen, put its electron, and I've put all the atoms down. So this hydrogen now has its stable 2, and the oxygen has its stable 8. So those non-bonding or lone electron pairs that are not connected to any hydrogens, those belong exclusively to the oxygen. So these are the ones over here, the one above and the pair to the left, those belong to the oxygen. They don't go hang out. There's no like sliding over. They don't go hang out with the hydrogens. They stay within the realm of that oxygen atom. So that way oxygen has its 8. So you might see it done like this. Dot, 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 dot. It would not be wrong if you put the 2 hydrogens on opposite sides or put them straight up and down. That would not be wrong. Just somehow you have an oxygen with 2 single hydrogens connected. Okay, so we did those 2. So you do this one. So you list the number of atoms in the molecule. So it's NH3. This is ammonia. Remember that you're writing the number of valence electrons. You don't care about the electrons that are in lower energy levels. They're full. Like they're full and stable. So when you look at carbon, you're not looking at 6. You're looking at the group number at the top because that's telling you the number of valence electrons. So you'll list the atoms, number of valence electrons, and the number of bonds needed. And the more that you do these, the less you feel the need to have to like list things out this way. But just to get you sort of started and familiar, where are you getting this from?
How did you, nitrogen?
So it's in group 5A. So look on, see at the very top,
Yes.
the number in front of the A tells you the number of valence electrons. Okay? So, yep, so that's where you're always going to get it. So like look where carbon is, it's 4A on the periodic table. So that's how I know that it has 4 electrons.
On four, what do you call it, valence?
So the valence electrons are the electrons in the outer shell, right?
If they're available to be shared or.
Right, those are the ones that need to create their stability of that stable 8, the octet rule. So hopefully you got these ones. So 5 electrons in nitrogen, so it needs 3 bonds to make 8. So you're remembering like the number of electrons plus the number of bonds is what's going to give you 8. Hydrogens, they're the oddballs. They only need 2 to have that stability, so 1 electron, 1 bond each. So that is why I'm going to start with nitrogen. Like I said, hydrogens are never going to be the center. You're always just going to add hydrogens or add fluorines and chlorines around the outside because they only ever form 1 bond. So you kind of always keep that in mind. So we're going to put the nitrogen down first. Nitrogen with its 5 electrons. You can put the pair wherever you wanted. I just go around that way. Then I'm going to add a hydrogen at each spot. So there's a pair that needs to go here, a pair to form here, and a pair to form here. Nitrogen has 8, hydrogens have 2 for stability. You might also see it drawn out like that. So if you see a dash, that represents a pair of electrons.
The 2 dots on top could be on the bottom.
Could be. Yep. It doesn't matter where you put that, the non-bonding pair or the lone pair. You could have them anywhere as long as you have a nitrogen and has 3 hydrogens connected and 1 non-bonding pair somewhere. Because these are not like stuck. These move. Okay. So molecules roll around. And molecules actually have a 3-dimensional structure. So kind of keep that in mind. The whole reason that I pushed lab 5 back is because we need to cover this kind of material and we need to get started into chapter 4. So this Wednesday we're doing lab 6. But we will talk about these and then you'll get to do them even more. So in practicing a couple of double bonds, triple bonds, these you see when you don't have enough electrons to make all single bonds and give those octets, then it requires that you make double bonds or even triple bonds in order to do that. So with this one, with oxygen, 6 electrons, right? See, it's in group 6A, 6 electrons. So that means it needs how many bonds to be 8? 2. So if we start with 1 oxygen, 1, 2, 3, 4, 5, 6, and we form a bond with another oxygen, 1, 2, 3, 4, 5, 6. I put everything down, right? I put my 2 oxygens down, and you notice the blue oxygen has 7 total. The red oxygen has 7 total. But I don't have any more electrons. You can't just randomly add those in. So if you get to this is when you have to form a double bond. So you will take this one and move them in between the 2 oxygens, showing that they're being shared between those 2 oxygens. So in that, I'll still have the 2 up here, the 2 to the right, but I'll have 2 in between with the red oxygen, and the same thing with the blue one. So I'll have the 4 that are non-bonding, but then I'm going to share 2 pairs. And when you go back and count, can you see that this has 8? Can you see that that has 8? The 4 in between, and then each one has 4 of their own. So that's the double bond. And you only do this if you get all of your electrons down and you don't have 8. Okay? So if you put all your electrons down and you're like, wait, I don't have 8 on this one or that one, that's when you know that you're going to form multiple bonds in order to achieve that stability. Carbon dioxide, CO2. Carbon is 4 electrons, oxygen is 6. Just from their group number. So in order to have 8, carbon needs how many bonds? 4, and oxygen 2. Right, so how many electrons plus the number of bonds, that's going to tell you how they're going to be stable. So I know carbon's going to have 4 bonds when it's all said and done. I know oxygen's going to have 2. So which one do I start with? Start with carbon. 1, 2, 3, 4. Then I have 2 oxygens, so just put an oxygen somewhere. I'll just put it over here because it'll fit in my space. 1, 2, 3, 4, 5, and make a pair. I always try to add to the atom that needs the most bonds, okay? Rather than putting an oxygen on an oxygen, that carbon is going to need 4 bonds. So I'm going to add or build to that atom that's in the center that needs the most bonds. So I'm going to put an oxygen over here. 1, 2, 3, 4, 5, and then 6. So I've put all my electrons down. I've used all my atoms. And I'm still short a couple of them. So notice like this oxygen's missing a pair or a single. It needs to form a bond. This oxygen over here needs to form another bond. And the carbon is actually missing 2. Those are all the electrons that I have to use. Now I have to move them around. So I can take this one and move it over here. And this one, move it over here. So moving those electrons over in between, take this electron and move them between the carbon and the oxygen. That's going to create double bonds between each oxygen and the carbon in the middle. So I end up with 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then in the center is the carbon. 1, 2, 3, 4. This oxygen can behave like it has its 8. This oxygen can behave like it has its 8. And this carbon has 4 on either side. Creates their stability. Double bond, double bond. And if I include the non-bonding pairs, those ones are in there. So between now and Wednesday, give these 3 a try. N2, nitrogen, it's another diatomic like oxygen. CH2O, formaldehyde, preservative. And then HCN, cyanide. Okay, they're all hydrogens and nonmetals. They're all covalent. See if you can figure out what their Lewis dot structure is, and we'll do those ones first. So the last thing I wanted to finish with, not that, is the fact that their naming's a little different. So sodium chloride, NaCl. When you're talking about covalent molecules, because covalent molecules can have sharing, we're not talking about transferring electrons, you can share in a lot of different ways. So you saw that carbon can share 4 single bonds, carbon can share with 2 double bonds, carbon can form a double bond and a triple bond. So what they found was you could have nonmetals and hydrogen forming a variety of combinations. So for example, you can have H2O, which everybody knows is water, right? Or you could have H2O2. What's that? Yeah, but what's its common name? It's peroxide, Okay, so water and peroxide, all they differ in their formula, they only differ by one oxygen. But one like bubbles on a cut and the other one just washes the cut. So really different properties. So they also found you had stuff like this. It's carbon and oxygen, but there's more than one way that they can combine. You can have carbon with one oxygen, or you could have carbon with two oxygens. So then, well, we can't just call that carbon oxide, because if we said carbon oxide, how would we know which one it is? And so covalent molecules have to have a number prefix. So they used a number prefix. The number prefix, these early ones, these ones you're familiar with, so these ones will start to give you sort of the hint. What is CO? Carbon monoxide. What is CO2?
So which one goes first?
So you always write the first element's name first. If
Okay,
the
so
first...
So if it was listed OC,
Yeah, that would...
I
be
know,
Orange
but you would
County.
say, like, oxygen,
It's out in Cali.
but okay, I get it. It's just based on
Yeah.
how you see it.
And honestly, 99% of the time, they actually write the element that needs the most bonds. Like the primary, the main one is oftentimes the one written first. Okay? So there you have carbon monoxide, carbon dioxide. H2O, dihydrogen. 1O would be monoxide. Just be glad you don't have to call it that. So there are traditional names that have carried through, but if you were going to name water, it would be dihydrogen monoxide. And H2O2 is dihydrogen dioxide. Okay, so you got the idea. What do you always put if there's two of them? Di. Okay, if there's one and it's the first element, you don't have to put mono. You only have to put mono if it's the second element. So that is why carbon monoxide is not monocarbon monoxide. If there's only one of the first element, you can leave it off. So, what's NH3? Yes. Nitrogen trihydride. No, not a hydroxide, because that'd be an OH. So nitrogen trihydride. So you still, it's similar to ionic because you use the whole name of the first element, first part of the second element plus IDE, right? Remember like with sodium chloride? So you're still doing that. The only thing that you've got to make sure that you add in is the number prefix. So here are the number prefixes. 1, mono. And remember, only the second element. 2, di. First element, second element, you use di. 3 is tri. So most people are like, okay, that's not terrible. 4 is a weird one. Tetra. Okay? So tetra means 4. Did anybody ever play Tetris? Do you remember it was the one you had a stick or an L or a Q or a block of 4? So that's where that comes from, is tetra comes from the Latin, Greek base that means 4. And so you would call 4 of whatever tetra. 5 penta, 6 hexa, 7 hepta, those start sounding like geometry, right? So that starts sounding like a pentagon, a hexagon, a heptagon. Then there would be an octagon, a nonagon, and then a decagon. So they start sounding very much like the old. I would say the only one that's kind of the oddball, some people have a problem with di because they want to say bi, because those both mean 2, but di is remember carbon dioxide, and you'll remember that one. But tetra, I would say, is probably the only oddity that people try to keep up with. Okay, so we did the first one. So what's this one? Yeah, carbon tetrachloride. This was used as a fire extinguisher material because it's really dense, and like they'd spray it on a fire and it would like smother the fire. The only bad thing is when this gets really hot, it breaks down and releases chlorine gas.
Great.
Yeah, so they kind of phased that one out because the firefighters were like, coming out. But it's really dense, and it like lays, it like forms a really nice layer and like smothers the fire because it takes oxygen away. So it doesn't allow oxygen near the flame, and so it makes it go right out. Okay, what about this one? So if you have penta, you just drop the A. So you would use pentoxide. Same thing if you had like a 6O, it'd be hexoxide instead of hexaoxide. Yeah. N2O4. Dinitrogen tetroxide.
It really just starts at 4, right? Once you drop the last other.
Yeah.
Cool.
Yeah, but monoxide. Like you dropped that O because you don't go monooxide. You don't put 2 O's. Then that'd be like strange. Okay? All right. So next time we will do a whole bunch more of these. Okay? And we'll also go back over and be like, okay, make sure you can tell ionic and covalent. Then we're going to talk about shapes. We're going to talk about polarity, molecules, and moles. And that'll finish up chapter 3. Okay? So it's like one more lecture and we finish that one up. Move on to chapter 4. Chapter 4 is fun. I mean, I like all this, but